Hello everyone. So, we will continue with the topic twist. What we are discussing is that the twist factor. Okay. So, twist factor we have discussed two different systems, one is in direct system, another is indirect system. Now, let us try to solve some numericals, very simple numericals we will try to solve here. Now, this is a very simple problem. We have say 4 different types of yarns, 4 different yarns of different count, okay. 20s, 30s, 40s and 50s any cotton yarn have same twist per inch, same twist, say 20 twists have been given with the all these yarns. Okay. Now, the yarn having maximum fiber obliquity is, which yarn will have maximum fiber obliquity? This is the question. Okay. Now, fiber obliquity means the theta, we are talking about the theta, and tan theta is proportional to the twist multiplier, and here if we can measure the twist multiplier of all these yarns, and the yarn with maximum twist multiplier will have highest fiber obliquity. Okay. So, this is an equation we know, and we know the equation here, twist per inch equal to twist multiplier multiplied by under root any. So, T m we can calculate by the formula T p I by under root any. So, here T p I is given for all yarn, it is fixed, it is a 20. So, we can calculate the twist multiplier for different yarn. So, twist multiplier for 20s yarn is 20 divided by under root 20, it is 4.47. For 30s yarn it has become 3.65, 40s yarn it has become 3.16 and 50s become 2.82. So, that means the yarn, coarser yarn, if we impart same twist, it will give us the higher twist multiplier. That means, as the yarn diameter increases or yarn becomes coarser, if we impart the same twist level, the twist angle will be more. That means, in among these yarns, this yarn of 20s count is hard yarn, most and softest yarn is the 50s count yarn, because it has got least twist multiplier, although amount of twist per unit length is same. So, the conclusion is that for the same twist level, higher twist multiplier is for coarser yarn. Okay. So, this is we have seen. So, 20s any yarn has maximum twist angle. So, maximum fiber obliquity, this is the answer. Now, next another problem here is the direct twist factor of 35 any yarn is 36 TPCM dot takes to the power half. This is the direct twist factor. The yarn count is 35 Nm, but here the unit is given in terms of tex. So, we have to convert this 35 Nm to tex, and the thing is given what is the approximate twist in terms of twist per inch. Okay. Here it is given twist per centimeter, it is asked the twist per inch. So, this is question part 1, and next is that if the diameter of the same yarn is 0.28 millimeter, what will be the approximate twist angle. So, this is the two part. The solution is that the data given, the yarn linear density is 35 Nm. So, let us convert it to text, it has become. So, text is the relationship is 1000 by Nm. So, 1000 by Nm means 28.57 text. Text we have got, and the twist factor is 36 is given here, and the equation is that twist per centimeter equal to twist factor by under root NE. So, we can calculate the twist per centimeter in the yarn. So, what is twist per centimeter? It has come out to be 36 divided by under root 28.57, it has become 6.73, and that is the twist per centimeter, and if we multiply it by 2.54. So, it will be your twist per inch. So, the answer is that first question is the yarn is having twist of 17.1 twist per inch. Now, second problem is that if the diameter of the yarn is 0.28 mm, what will be the approximate twist angle? Now, the solution here is that the formula we know, tan theta equal to pi d t. Here pi is d is known, given to 0.28 millimeter, and t is known that we have calculated earlier. So, diameter we have converted in terms of centimeter, because it is a twist per centimeter was given. So, twist per centimeter we have got 6.73 twist per centimeter. So, tan theta we can calculate pi multiplied by diameter 0.028 multiplied by twist per unit length twist per centimeter. So, it is coming out to be 0.5832, and theta is tan inverse 0.5832, it is coming out to be 30.25 degree. So, that is the twist angle of the yarn. So, in this way we can solve different problem related to twist in the yarn. Okay. These are very simple, and if we understand the concept of twist multiplier, we can solve many problems. Okay. And this is very actually practically it is used in industry. Okay. Now, other terms which is very widely used in industry, and people normally get confused with this term. One has to be very careful in using these two terms, and where do we use these terms? These terms are related to twist, but it is a twist contraction. Okay. As the yarn gets twisted, like this is the fiber, this is the strand, and it is twistless, and when it is twisted, the length, suppose it is a length L0, this length will get contracted because of the inclined helix of the fiber. Okay. So, this is the L1, so L0 is more than L1, that is the contraction. This is the contraction, and the knowledge of this twist contraction and retraction helps in maintaining the draft in the spinning process properly. So, we must know the amount of contraction, at least rough idea which we must have, so that we can properly set the draft. Otherwise, if we set the draft, suppose we want to have a yarn of say 30 ticks, okay, 30 ticks say from a roving of say 900 ticks. we have a roving of 900 takes and we want to get 30 takes yarn. Now, in that case in the ring frame drafting system we have set the draft 900 by 30. So, 30 draft we have saved. So, ultimately what will happen if we set 30 draft. So, it is not the 30 takes which we are getting, it is not the takes of the final yarn, it is the takes of this strand which is coming out from the front roller nib. Okay. But finally, this has shortened to L1, that means it has contracted, and the takes means the unit, the constant for constant mass, what is the length, that means the mass is constant, the length, if length is actually contracted, that means the takes value, final takes value will be more than this value, it will be somewhere higher than this takes value. That is why we have actually done some wrong calculation, and it will be say suppose 31 takes or something, 31, 32 takes somewhere higher than this, and that is due to that we have not taken into consideration of contraction. We do not have any knowledge of contraction. So, if we have a knowledge of contraction, then we can actually set a draft of little bit more than this higher draft. Suppose we will draft more than this draft, which is maybe say 31, 32 draft we will set, and if we set the draft more than this, the fiber takes, the strand takes will not be 30, it will be less than 30, it will be say 29 or something takes. So, this takes if we get, then after contraction it will come out to be close to 30 takes, which is our target area. So, that is why the twist contraction is concept is extremely important for the setting of draft. So, contraction factor, there are two factors, one is contraction factor, the factor by which the draft is to be increased to maintain the yarn count due to twist contraction. That is the, and contraction factor, the CY is expressed as the length of 0 twisted yarn divided by length of twisted yarn. So, that is why, so 0 twisted yarn and length of twisted yarn, and length of twisted yarn, if it is there is no twist, if there is no twist in the yarn, so contraction factor will be, it will be 1, and if there is a infinite, suppose it is a twist is such that it has the contracted and contracted, ultimately it has become 0 theoretically. So, the contraction factor will be infinite. So, the range of contraction factor is that it is a from 1 to infinity. So, that is how we can measure. So, it starts from 1 when there is no contraction, okay, and the setting of draft in the ring frame is that the nominal draft in the ring frame is twisted yarn count by roving count. That is how we set the nominal count, and actual draft which we have to set, it is basically it is more than that, because ultimately yarn count is we know that is the count it is required. Okay. Here it is a indirect system, in direct system roving takes by yarn takes. So, in that way the actual draft will be, we have to multiply the nominal draft by the contraction factor. So, we must have knowledge of contraction factor, so that we can set the actual draft in the ring frame. Similarly, the retraction factor is that it represents the fractional decrease in length or increase in linear density of continuous filament yarn during twisting. So, this retraction factor is normally used in filament, multi-filament yarn. So, it is a fractional decrease. So, mean untwisted length by twisted length divided by twisted yarn length. Okay. That is the retraction factor. So, we must have some knowledge of contraction and retraction, then we can actually set the draft, proper draft or proper twist level we can set, because retraction factor is important, because if we know the twist, if we know the retraction factor, then we can calculate the length of the filament, otherwise the filament length calculation will be wrong. So, that calculation is important here, but in staple yarn it is the draft. So, the difference is that in staple yarn the length calculation is not done by the twist, there it is done by the delivery rate, okay. But here it is a length which we have already produced the filament twisted, and before twisting we know the filament length, and if we know the retraction factor we can actually predict what will be the actual length of twisted filament. Okay. Now, we will discuss the techniques of measurement of twist. Okay. There are different techniques available. So, first is that direct counting method. Okay. This is the it is a simplest method where we actually untwist the yarn. The method is to untwist the yarn, whatever twist available in the present in the yarn, and to count how many turns are required to make it 0 twisted. So, we have to keep on untwisting till it has become 0 twisted. Okay. A suitable instrument has 2 jaws at a set distance. Okay. The distance is known, and out of this 2 jaws, one jaw is only laterally movable, it does not rotate, it moves to set the required test length, and another jaw which rotates just to untwist the yarn up to the level of 0 twist. Okay. So, a counter is attached to the rotating jaw just to count the number of turns. Samples are conditioned in the standard testing atmosphere before starting the test. Now, this is the instrument where this is the movable jaw which moves laterally, okay, and the scale is there which determines the test length. Suppose we want to test at say 10 centimeter length or say few inch length, okay, 10 inch gauge length. So, we move this jaw. First what we have to do? We have to fix the yarn end at the rotatable jaw, okay, that we are fixing. Then we set the movable jaw, the length, test length we are setting. After that we start the count this untwisting by rotating the handle, okay, and where depending on the direction of twist we can use the counter for S twist and Z twist, and number of turns are counted, it is a straightforward, and where a standard dead weight is placed hanged, because to remove the undue crimp in the yarn, okay, to make the yarn straighten, then the jaws are tightened and then start rotating. Now, the testing is started at least 1 meter from open end of the yarn, that we have discussed during sampling. We have to take the yarn at least 1 meter from the away from the end, because at the end if we take, that may give wrong result because of the torque present in the yarn. Those at the end it will get untwisted. Standard tension, it is 0.5 centinewton per tex is used. So, when the yarn is being clamped in the instrument, the twist is removed by turning the rotatable clamp until actually possible to insert the needle. Okay. Now, the yarn when it is twisted, in the twisted yarn, this is the twisted yarn, and depending on the direction of twist, if we untwist this one, ultimately the fibers will become twistless and will stop there, and then we will actually insert some pin, and if the pin moves smoothly, that is the point where we will stop, and that we have to do by trial and error method. And once the individual the pin moves, then the non rotatable the twist is removed by turning the rotatable clamp until it is possible to insert a needle between the individual fibers. So, individual fiber, between the individual fiber we have inserted the needle at the non rotatable clamp. So, other side we have inserted and the traverse it across the rotatable clamp, that we will try to traverse, and if it moves smoothly, then there will be, it will be twistless. In that, then we can count the number of twists. So, we can use a magnifying glass, okay, just to see the alignment of fiber. It is for single yarn we need the the magnifying glass just to see the fiber, but for double yarn we do not need, because we can simply pass the needle. Okay. Next is that continuous twist tester. The principle is exactly same here, but the difference is that here the yarn directly from the package will be tested, and it will be again after testing again it will be winding on the another package. It is a continuous process, but it is, we cannot say continuous, it is intermittent process, but the strand of yarn is continuous. So, we do not take the cut yarn. Okay. The straightened fiber principle is also used here. So, we use the same principle as we have used earlier. The yarn pass from it passes from the same package through a guide, through a non rotating jaw, through a rotating jaw, and finally, it is winding on a package, on a drum. So, this is the principle. Here this A is the, it is a base. Okay. Here it is a base of the instrument, B is the peg on which we place the bobbin, okay. C is the yarn package, and this is the D is the guide, yarn guide, E is the here E is the lens, magnifying lens. We can see the whether its fibers are parallel or not, and here F is the fixed jaw. This is the fixed jaw here. Here the thing is that fixed jaw, in earlier case we have seen the fixed jaw can move laterally, but here the fixed jaw is fixed, it does not move laterally. So, this is the fixed jaw, and the rotatable jaw, this one it can move laterally and also it rotates here. So, rotatable jaw is this is the G is the rotatable jaw, H is the counter, it counts the number of turns, H is the counter, I is the handle, we can just rotate the untwisting takes place, J is the winding drum, and K is the specimen. This K, length of K is actually adjusted by moving this movable jaw. Okay. It is movable as well as rotatable jaw. Assuming that 1 inch length k of the yarn is gripped between the jaw, the twist is taken out and the number of turns are noted. So, if we test 1 inch length, then simply by untwisting directly the number of turns, we can get the twist per inch. The handle is then turned until the counter reading is again 0. Okay. Then and so, after twisting, then again we will have to bring it to 0 for the next test. The spring loaded jaw of the rotating clamp. So, the clamps are spring loaded, are opened and clamp moved to the other clamp, this rotating clamp moved to forward to touch the fixed jaw. So, here the system is that this is actually it is moving here. So, that it is earlier there was a testing was there, then it is actually this clamp is moving towards the fixed jaw, and with the it is once it is touching, that means there is no yarn, that in that case then we clamp it at the rotatable jaw, and after clamping again we move towards right side. So, that the required distance is there in between these jaws, and during that time this jaw F, this jaw it is loose. So, that yarn is unwound from this package C, and the specified length k is once it is reached, then we stop this jaw, the movable jaw, then it is tightened, the jaw is tightened, spring loaded tightened, and by that time once it is moving here, the yarn is continuous yarn. So, this there will be slackening here, that slackening we can manually wind again. Okay. So, after that winding, that the specimen is ready for testing, then we will start the unwinding and measure the twist. So, the fixed jaw is then opened, rotating jaw rotating clamp is pulled back to the working position with which pulls 1 inch new test sample, and the drum is allowed to take up the slack yarn. Okay. Fixed clamp is again closed, which is now ready for the next test. Okay. So, this way this continuous testing take place. So, from one package we can test very quickly a number of tests. Okay. Next principle is it is called untwist twist method. So, untwist twist method, or another term is it is called twist contraction method. So, this is the system where the knowledge of twist contraction is being used, because here the principle is that initially the yarn is twisted, and it is assumed that yarn, whatever length of yarn, twisted length of yarn L T, it is less than that of the untwisted yarn. Now, once we untwist the yarn becomes fibers becomes parallel, the yarn length is increased. So, L 0 twisted length. Now, after this 0 twisted length, it has become 0 twist, then we will not stop here, we will keep rotating that jaw, and the yarn will be twisted in other direction. So, suppose this was in this twist was in z direction, here it is a 0 twisted, no twist, and here then it will be s direction. We will keep continuing the twisting till the initial length is reached. So, this was a higher length. So, initial length, this length is same length is this. So, this is become LT. So, what happened here, the assumption is that the twist, the during untwisting, the length is increased, and suppose you are giving the twist T here. So, we are rotating it to have, so T turns we are rotating here, and if we rotate the same turn T, the yarn will contract again to the same extent. That is the assumption here, and this is actually for most of the staple yarn, this works basically, because here the during twisting in other direction, it again gets contracted. Okay. So, that means what we are doing, we are imparting the double the twist, 2 T twist we are imparting, 2 T turn we are imparting, and then we can do calculation to get the twist. So, if we know the length say x length. So, for x length, so this total turn we are if we know, and if we divide it by 2, that will give us the actual turns per unit length. Okay. So, here the system is that this is the pointer with certain minimum load of tensioning, and the pointer is in the yarn length is selected in such a fashion that this is the length here, that the pointer the yarn is pulled, the pointer is being pulled by the yarn, so that it comes to the 0 segment, 0 position, it is a 0 mark, it has reached, pointer is inclined, and the yarn is under tension of that this dead weight, some minimum load is there. Okay. Now, what happened if we start untwisting the yarn, then the yarn gets extended, then pointer will be vertical, pointer will never come in other direction, because the yarn is slack, and this is the condition here, and in between when the pointer is straight, after that maybe at certain point, may not be immediately, after certain point, still if the twist is there, the yarn will become slackened here. Then we will continue rotating this handle in the same direction, and after that, after 0 twisting, when the 0 twist, here we will not be able to actually point out the 0 twist condition, but if we continue after it crosses the 0 twist condition, then yarn will again start contracting. So, and we will continue rotating it till the pointer reached to the 0 position, which actually shows the initial length, it has reached to the initial length LT as we have seen. So, this method is based on the assumption that with the increase in twist, the yarn contracts in length. When the twist is removed, the length will reach to its original length. Okay. So, original 0 twisted length, and when the yarn is again retwisted in the other direction, that means we will continue rotating in the other direction to the same extent, the yarn will reach again to its initial contracted length, that is the assumption, and suitable for staple yarn. So, we normally do not use for filament yarn, because filament yarn twist is very simple measurement. We can use the first method, we can actually get the direct twist 0 twist condition, because here 0 twist condition identification is very difficult. Okay. That is why we use this one. the yarn is kept under the same tension, it is a small tension we measured, and this tension is normally constant, okay, for set of yarn, and has a nominal length 10 inch length we keep. As the twist is removed, the yarn extends and pointer assume vertical position, and so removing tension is there. Eventually all twist is taken out, but the jaw is kept rotating in the same direction, bringing the pointer back to its original 0 mark again, and the total length of the yarn was 10 inch if we assume, then the total number of turns recorded, the bringing it to 0 mark, if we divide it by 20, we will directly get twist per inch. So, that is because we have to divide by 2 times of that m, because it is 2 multiplied by 10, because it is rotated in 2 times. Now, there is a limitation here. Limitation is that it is this is not useful, this system we cannot use for all the staple yarn. We can use for mainly for ring spun yarn. And that too for only gray yarn, not even we should not use for say scoured or processed yarn, bleached yarn, and only ring spun yarn is, it gives a correct result, very close result, accurate result it gives. But if we try to use other yarn, say rotor spun yarn, rotor spun yarn main problem is that it has got typical structure with the fiber, wrapper fiber. As it has got wrapper fiber, the untwisting is a problem. If it does not get untwisted, and once it is not getting untwisted, so we cannot, it cannot actually extend, it does not extend, or even the 0 twist condition is not possible. So, effectively rotor yarn is the extreme example, we cannot normally measure. Measuring twist in rotor spun yarn is difficult, but we can take example of scoured cotton yarn. In scoured cotton yarn, the thing what it happens, the during scouring the fibers get little bit distorted in the structure, and the whatever the wax material, this materials comes out from the fiber surface, and fiber to fiber friction increases, and there may be some clustering occurring. So, fiber gets stick together, and if we try to use this method of untwisting twisting, that proper extension of proper removal of twist may not be there, 0 twist condition may not be there, because there of the some entanglement, some clustering of fibers. So, this may give some wrong result when we use some processed yarn. This is only, this will give correct result when we measure the fibers which are easily separable. Okay. Now, this problem is there are many yarns, not only this, like woolen yarn, woolen some processed yarn. So, fibers sometimes gets actually they have some have stick together, or they have some high friction, some clustering takes place. So, for this type of yarn we cannot use the untwist twist method, but there is another method which is known as multiple untwist twist method, where the errors at different stages get actually even out. So, that multiple twist method, in the earlier method of untwist, the number of turns to return the yarn to its original length is not the same as the number of turns to take the twist out. So, that is possible mainly for different types of yarn, but even for raw cotton yarn also this type of errors takes place. So, it has been observed that a number of turns are different, that is due to the reversal of the twist. So, this actually generates some error in the reading. In spun yarn, the distortion becomes permanently set into the fiber. So, sometime what happened, so in cotton yarn, if we actually set the twist by steaming or some other treatment, due to twist setting, not only cotton yarn, but for say synthetic yarn we normally set twist. So, the fibers get actually permanently set in the distorted condition, and untwisting becomes actually problem, and the elongation due to untwisting and retwisting, contraction due to retwisting, it is not same, it actually adds some error. This is particularly a problem in yarn made of wool fiber. So, that in case of wool fiber we cannot use earlier method. In this method the yarn is untwisted and retwisted back to its original length as in the normal test, and the number of turn A is noted. So, that is done just like earlier test, and this twist is number of turns is noted. This is untwisted, expected 0 twisted, and then again we are continuing to retwist, this is A. Okay. Now, after that the value A contains an unknown error D, this is the D which is unknown, we do not know the error value, unknown error. Without the counter being zeroed, we are not zeroing the counter, the direction of turn is reversed. So, we have reached to the extreme point, then we are reversing it again. The yarn untwisted and twisted back to its original length again. Okay. So, this again we are doing the same process, okay, untwisting and twisting back again, and it is adding another error D 2. So, if it adds D 1 D 2, it has become B, B is the error. Okay. Now, we will repeat the same process again third time. This is to bring back the yarn to its original condition. However, owing to the errors, the counter will show a small number of turns instead. So, after reaching there, so counter will not show 0, it will show some value, okay, which is actually error, and this reading is taken as B, okay, which is the due to the errors D 1 and D 2. Okay. Ideally B should be 0. So, that is why, so this error is there, and then by untwisting and retwisting a third time, the counter reading is C, that we have reached, obtaining which contains the errors D 1 and D 2 and D 3. So, C has reached. So, the formula which gives the A minus 2B plus C equal to 4x, where x is the number of turns in the length of the yarn, total length of the yarn, what is the number of turns. The method relies on the error D 1, D 2 and D 3 becoming progressively smaller. So, that it D 1 is larger, then D 2 is smaller, it will become smaller. So, that the remaining errors in the above equation is the difference between D 2 and D 3, which can be ignored. So, that is ignorable. So, in this way we can test the yarn where the just to actually eliminate any error due to the fiber set of the yarn. Okay. Another test is which is automatic twist tester. This is simple like other techniques, just automatic. This method depends on the untwisting twisting principle, and as it cannot determine the fiber straightening automatically. So, it's only earlier method is manual, this is automatic method. Now, twist in the plied yarn. Okay. So, in ply yarn measurement of twist is very simple. We use simple counter to untwist the ply, and we can use the pin just to once it is passing through, then it's a we can count the number of twists, but the concept of plying is little bit tricky. Okay. In plied yarn, first there is twist in the individual yarn and making of the ply, and the secondly there is a twist in that holds the individual ply together. Now, here it is that this is individual yarn, individual yarn. Okay. This is Z twisted. Now, we are plying this to yarn to form say 2 ply yarn. Now, where if we ply this yarn in S direction, this will be called as S over Z, and once we impart twist in S direction, suppose in Z direction the twist is say twist per unit length is say 20. Okay. In S direction, when we start twisting in the S direction, so per twist, per one twist there will be a reduction of twist in single yarn. So, ideally if we apply 20 twist in 2 ply twist 20 in S direction, then what will happen? Ideally the fibers in the individual yarn will look like this. This is 2 ply yarn, what does it show? The fibers are parallel. It should be ideally parallel, that means one twist in other direction in plying will actually reduce one twist in the single direction. So, normally we do not go up to this point. In normal application we use typically around say 70% of the single yarn twist. So, if it is 20 twist per inch, so we impart say 14 twist per inch, so that we get the proper feel, proper material. Okay. One can always get this value. So, by controlling, by adjusting ply twist, we can control the characteristics of the yarn. Okay. In ply yarn, firstly there is a twist in the individual strand making of the ply, and secondly the twist in the 2 ply condition which holds the strand together. Okay. If the twist in the single strand is required to be measured. Now, how to measure the twist? Now, here in the single strand, ideally if it is 20 twist and 2 ply if we impart 14 twist. So, in 2 ply it is become 14 twist, but single ply the twist is here it is a say 6 twist, 20 minus 14, 6 twist per inch. This 6 twist per inch is there, but if we want to measure the twist in the single yarn here, how do we measure? So, this 6 will not be there again. Again if we untwist, once we untwist, then for every twist untwist, one twist will be added again to the because we will be untwisting in the again in the z direction. The 2 ply yarn, once we try to untwist, so it will apply, so it will keep on adding the twist in the single thread, and once this plied yarn becomes parallel. So, when there is no twist, then we can take out the strand and holding, and then we test the individual yarn twist again. So, here although untwisting is taking place, but once we are trying to take out the yarn individual yarn, again we are imparting the same twist. Okay. So, if the twist in the single strand is required, the yarn can be analyzed by first removing the folding twist, then cutting out the individual yarn, leaving the one strand whose twist is to be measured. Okay. That strand we can twist. Now, there are two types of twists are there. One is just reverse order twist, which is more common in nature, like S over Z or Z over S, because here if we have say S over Z or Z over S, the advantage is that the individual yarn twist gets reduced. So, yarn becomes balanced. Balanced means that there will not be any residual torque present in the yarn, but for some special application what we do Z and Z, then we apply Z twist again on this yarn. If we apply Z twist again in 2 ply condition, in that case what we will get, we will keep at suppose 2 ply condition, what we are applying say 10 twist per inch. What will happen? The single thread, single strand will have very high twist of 20, this 20 plus 10 of single. So, 30 twist per inch will be there in single strand, but in the say in double strand there will be 10 TPI. So, this will give a yarn of very special characteristics. Single yarn has got very high twist, this will start having some crepe effect, and this will give us a special effect in a fabric, and there are various applications where we use this type of effect in the yarn, because the application of very high twist in single thread sometimes creates problem in one stage. Suppose we want to create impart a twist 30 TPI or 40 TPI in ring frame, the impact is that first is that its productivity of ring frame will go down drastically, and also the yarn will have so snarling tendency, we cannot actually process the yarn in next process. in winding or twisting it is not possible. So, the technique is that if we want to have a crepe like effect, we and in 2 ply we must go for this technique Z over Z or S over S. That is the normal technique used in the industry to get different effect. We do not apply twist in fast go in ring frame, okay, or in spinning process because of the two reasons. One is productivity, another is handling the yarn in high, it will be highly twist lively. Okay. So, we will stop here, we have completed the twist measurement section, and in next class we will start a new topic. Till then, thank you.